Imagine descending through layers of ocean so deep that sunlight has never touched them, where the pressure could crush a submarine. Yet life not only survives but flourishes in ways more beautiful and peaceful than anything found on the surface. Tonight we're going to journey to the deepest places on Earth, where gentle giants drift through eternal darkness, where living lights dance like stars in an underwater sky, and where time moves so slowly that a single creature's lifetime can span centuries. In the abyss, 3 miles below the surface, where we sit comfortably tonight, there exists a world of profound tranquility. Here, in temperatures just above freezing and under pressure that would flatten most surface dwellers, creatures have evolved not for speed or aggression, but for patience, efficiency, and a kind of meditative grace that puts our hurried surface world to shame. This is the realm of the gentle giants, creatures so large they dwarf school buses, yet so delicate they seem to be made of living water. Jellyfish, the size of dinner tables, pulse through the darkness with movements so slow and rhythmic, they seem to be breathing with the ocean itself. Tube worms as tall as trees sway in currents warmed by the Earth's own heart, creating underwater forests that have grown in peaceful solitude for thousands of years. But before we descend into this otherworldly realm of living silence and bioluminescent beauty, settle yourself into comfort. Let your breathing slow to match the patient rhythm of the deep ocean currents. Allow yourself to feel the weight of the peaceful darkness that surrounds these deep-sea creatures, not as something frightening, but as a soft blanket that has cradled life for hundreds of millions of years. I do hope this journey into the abyss isn't so mesmerizing that it keeps you awake, but if it does, you'll drift off with visions of creatures that seem to have been designed by dreams themselves. Transparent beings that glow with their own inner light, ancient fish that move like living meditation, and gardens of life that bloom in eternal night. Close your eyes if you'd like, and imagine yourself in a submersible slowly descending through the water column. Above you, the last traces of sunlight fade to black. Below you, an alien world awaits, not hostile or barren, but peaceful beyond imagining, populated by creatures that have mastered the art of living slowly, gently, in harmony with forces that would overwhelm anything that moved too fast or burned too bright. Tonight, we'll discover that the deepest parts of our planet are not empty wastelands, but thriving ecosystems where life has learned to create its own light, to find food in the rain of organic matter that falls from above, and to build communities around vents that speak directly to the molten heart of the earth. We'll meet creatures that challenge our assumptions about what it means to be alive, to be intelligent, to be beautiful. This is the story of life in slow motion, where every movement is deliberate, every flash of light is meaningful, and every creature is perfectly adapted to a world that exists in perpetual twilight. It's a realm where bigger often means gentler, where the largest creatures are filter feeders that harm nothing, and where the most spectacular displays of light are not aggressive warnings, but gentle communications between neighbors in the dark. So breathe deeply. Let your thoughts settle like marine snow drifting toward the seafloor, and prepare to enter a world where pressure creates not crushing force but profound peace, where darkness is not empty but full of quiet wonders, and where the rhythm of life beats so slowly that each heartbeat seems to last forever. Our journey begins at the surface of the ocean on a calm, moonless night. Above us, stars scatter across the dark sky like scattered diamonds. Below us, the water stretches down into an abyss so deep that Mount Everest could be completely submerged with room to spare. The ocean's surface is mirror still, reflecting the starlight in gentle ripples that seem to breathe with the planet's own rhythm. As we begin our descent in our imaginary submersible, the familiar world of the surface quickly fades away. The first 100 feet still hold traces of the sun's energy, stored in the plankton and small fish that form the base of the ocean's food web. But even here, as twilight settles into the water, we can sense the profound changes that await us in the depths below. At 200 meters down, we pass through what marine biologists call the twilight zone, where the last whispers of sunlight struggle to penetrate the increasing darkness. Here, the water temperature begins to drop noticeably, and the pressure starts to build, not oppressive yet, but noticeable, like the gentle weight of a heavy blanket settling over everything. The creatures we encounter in this transitional zone, hint at the wonders that await us deeper down. Schools of lanternfish begin their nightly migration upward, their bodies dotted with photophores, tiny organs that produce living light. They move in coordinated clouds, creating underwater constellations that pulse and shimmer as they rise toward the surface to feed. As we continue our descent, passing through 500 meters, then 1,000, the water around us transforms from the deep blue of the surface zones to an increasingly profound blackness. Yet this is not the empty darkness we might expect. Our submersible's lights reveal a constant gentle snowfall, marine snow, the continuous drift of organic particles falling from the productive surface waters above. This marine snow is like manna from heaven for the deep-sea creatures below, composed of dead plankton, fecal pellets, mucus and other organic debris. These tiny particles aggregate as they fall, sometimes forming larger clumps that drift down like underwater snowflakes. Some particles will take weeks to reach the deepest ocean floors, providing sustenance for creatures that have never seen sunlight, and never will. At 2,000 meters, we enter what oceanographers call the bathypelagic zone, and here the ocean's character changes completely. The temperature stabilizes at just a few degrees above freezing, remaining constant year-round. The pressure has increased to over 200 times that at sea level, enough to compress any air-filled space to a tiny fraction of its surface volume. Yet for creatures born and adapted to these conditions, this pressure is not crushing but comforting, providing the dense supportive environment they need to maintain their body structures. The water here has a quality unlike anything at the surface. It moves in vast, slow currents that take centuries to complete their journeys around the globe. Deep water that sank in the North Atlantic might not see the surface again until it wells up in the Pacific decades later. These currents carry not just water, but nutrients, dissolved gases, and even microscopic life forms on journeys that span continents and generations. Sound behaves differently at these depths as well. The pressure and temperature create acoustic conditions that allow sounds to travel for thousands of miles. Whale songs can echo across entire ocean basins, and the low-frequency calls of deep-sea creatures might be heard by relatives hundreds of miles away. The deep ocean is not silent. It's filled with a symphony of sounds that we're only beginning to understand. As we descend past 3,000 meters, we enter the abyssopelagic zone, the true abyss. Here the seafloor is still miles below us, but we're beginning to encounter the creatures that make the deep ocean their permanent home. The pressure at this depth is crushing by surface standards, over 300 times atmospheric pressure. Yet the creatures here have evolved bodies that are perfectly balanced with their environment. Many deep-sea creatures have no gas-filled swim bladders like surface fish. Instead, they maintain their buoyancy through specialized lipids and proteins that remain stable under extreme pressure. Their bodies often appear gelatinous and translucent, not because they're weak, but because this body design is perfectly suited to their high-pressure environment. The water column around us begins to reveal its hidden residence. A siphonophore, a colonial organism related to jellyfish, drifts past our lights like a living constellation. These creatures can be among the longest animals on Earth, sometimes stretching over 100 feet, yet they're so delicate and ethereal that they seem more like living dreams than biological reality. The bioluminescence we begin to see at these depths serves purposes very different from anything on the surface. In a world without sunlight, creatures have evolved to create their own illumination through chemical reactions within specialized organs. Some use light to attract prey, others to communicate with potential mates, and still others to confuse predators or create decoy displays. Each flash of bioluminescence tells a story. A brief blue flash might be a startled creature trying to confuse a predator. A steady green glow could be a deep-sea anglerfish using its luminous lure to attract prey. Patterns of lights along a creature's body might be a mating display or a form of species recognition in a world where visual contact is rare and precious. The temperature at these depths remains remarkably stable, usually between 2–4 degrees Celsius. This consistency is one of the factors that makes the deep ocean such a stable environment. While surface waters fluctuate with seasons and weather patterns,
The deep ocean provides a constant, predictable environment that has remained essentially unchanged for millions of years. At 4,000 meters deep, we begin to approach the true abyssal plains, vast, flat expanses of seafloor that stretch for thousands of miles with less topographic variation than the surface of the moon. But even here, life has found ways to thrive. The seafloor is carpeted with sediments that have accumulated over millions of years, creating a soft, muddy substrate that supports a remarkable diversity of bottom-dwelling creatures. The pressure at this depth exceeds 400 times atmospheric pressure, yet this crushing force has created, paradoxically, an environment of profound peace. Movements here are slow and deliberate. There's no rushing in the abyss. Energy is too precious, food too scarce, and the environment too stable to reward rapid, wasteful activity. As we settle onto the abyssal seafloor, our lights illuminating a small circle of the vast underwater plain, we find ourselves in one of Earth's most alien yet tranquil environments. The sediment beneath us contains the remains of countless microscopic organisms that lived and died in the surface waters above over periods spanning millions of years. We're sitting on a library written in the language of deep time, where each layer of sediment represents epochs of Earth's history. Here, in this place of eternal darkness and crushing pressure, we begin to encounter the true gentle giants of the deep, creatures that have adapted to life at the very bottom of the world, in conditions that would seem impossible to surface dwellers, yet which support some of the most remarkable and peaceful life forms our planet has ever evolved. The silence here is unlike anything experienced on the surface. It's not the absence of sound, but rather a profound cathedral-like quietude that seems to absorb and soften every noise. In this acoustic sanctuary, even the gentlest movements take on a meditative quality, and every encounter with life feels like a privilege, a glimpse into a world that operates by rules entirely different from our own.
In 1977, a team of marine biologists was exploring the Galapagos Rift, a volcanic ridge on the Pacific Ocean floor, when they made a discovery that would revolutionize our understanding of life on Earth. As their submersible Alvin descended to depths of over 8,000 feet, the scientists expected to find the barren, lifeless seafloor that deep ocean exploration had revealed everywhere else. Instead, they discovered something that seemed impossible: an oasis of life thriving in the most hostile environment on the planet. Rising from cracks in the seafloor, they found towering structures that looked like underwater smokestacks, belching superheated water rich with dissolved minerals. Around these hydrothermal vents, life flourished in abundance that rivaled the richest coral reefs. But this was life unlike anything they had ever seen. Life that had learned to harness the chemical energy of the Earth itself. Giant tube worms, some reaching lengths of 8 feet, swayed gently in the mineral-rich currents like an underwater wheat field. These remarkable creatures had no mouths, no stomachs, no digestive systems at all. Instead, they had formed a partnership with bacteria that could convert the toxic hydrogen sulfide from the vents into usable energy. The worms provided shelter and nutrients to their bacterial partners, while the bacteria provided all the food the worms needed to grow to enormous sizes in this seemingly barren environment. Dr. Robert Ballard, who was part of that historic expedition, later described the feeling of discovery. It was like finding an alien world on our own planet. Here, in the deepest, darkest parts of the ocean, we found not just life, but abundant, thriving ecosystems that operated on principles we didn't know existed. The hydrothermal vents created their own weather systems on the seafloor, superheated water, reaching temperatures of over 750 degrees Fahrenheit, mixed with the near-freezing deep ocean water, creating columns of shimmering water that rose like underwater tornadoes. The mineral-rich water precipitated metals and sulfides as it cooled, building the chimney-like structures that could grow several feet in a single year. But it wasn't just the tube worms that fascinated the scientists. The entire ecosystem around the vents operated on a completely different energy source than the rest of life on Earth. While surface ecosystems depend on photosynthesis, the conversion of sunlight into chemical energy, these deep-sea communities had evolved to use chemosynthesis, deriving energy from chemical reactions involving sulfur, methane, and other compounds that would be toxic to most surface life. Giant clams, some over a foot long, clustered around the edges of the warm water flows. Like the tube worms, these clams harbored chemosynthetic bacteria in their tissues, allowing them to thrive in an environment with no sunlight and very little food falling from above. Their shells, pristine white in the mineral-rich water, created underwater gardens that seemed almost too beautiful to be real. White crabs, blind from generations of living in absolute darkness, scuttled across the seafloor with a peculiar grace. Their movements were slow and deliberate, conserving energy in an environment where every calorie was precious. These crabs had evolved not just to tolerate the extreme conditions around the vents, but to thrive in them, feeding on the bacteria that grew in the mineral-rich water, and on the occasional piece of organic matter that drifted down from the world above. Perhaps most remarkably, the scientists discovered that these vent ecosystems were incredibly dynamic. Unlike the stable, slow-changing environment of most deep-sea habitats, hydrothermal vents were subject to sudden changes. Volcanic activity could shut down one vent while opening new ones nearby. Earthquakes could alter the flow of superheated water or shift the locations of the mineral deposits. Yet life had adapted even to this instability. Many vent species existed as floating larvae that could drift with the deep ocean currents until they found new vents to colonize. It was a form of biological island hopping, with species maintaining connections across vast distances through their ability to disperse and re-establish populations at newly formed vents. The discovery of hydrothermal vent ecosystems fundamentally changed our understanding of life's possibilities. Here was proof that life could exist without any dependence on the sun, that entire ecosystems could thrive on chemical energy alone. The implications were staggering, not just for understanding Earth's biology, but for considering the possibility of life on other worlds. Scientists began to realize that similar conditions might exist on Jupiter's moon Europa, or Saturn's moon Enceladus, where liquid oceans beneath ice crusts might harbor hydrothermal vents. If life could thrive in Earth's deep ocean vents, perhaps it could exist in the hidden oceans of other worlds as well. The bacteria that made these ecosystems possible proved to be among the most ancient forms of life on Earth. Genetic analysis revealed that chemosynthetic bacteria were likely among the first life forms to evolve. Billions of years ago, when Earth's atmosphere was very different and sunlight couldn't penetrate the thick, toxic atmosphere, the deep ocean vents might represent not just an alien ecosystem but a window into life's earliest origins. Dr. Cindy Lee Van Dover, a marine biologist who has spent decades studying hydrothermal vent ecosystems, describes the experience of visiting these underwater oases. There's something almost spiritual about descending to these depths and finding life flourishing in conditions that seem impossible. It's a reminder that life is far more creative and resilient than we ever imagined. The tube worms became symbols of this resilience and creativity, growing in dense clusters around the vents. They created underwater forests that swayed gently in the current. Some individual worms were estimated to be over 100 years old, having grown slowly but steadily in their chemical oasis. Their bright red plumes, filled with hemoglobin to help them process the chemicals in the vent water, created striking splashes of color in the otherwise monochrome deep sea. The discovery also revealed the importance of symbiosis in extreme environments. The partnership between the tube worms and their bacterial symbionts was so complete that neither could survive without the other. The worms had essentially outsourced their digestive systems to their bacterial partners, while the bacteria had found the perfect habitat within the worm's tissues. This symbiotic relationship became a model for understanding how life might evolve in extreme conditions anywhere in the universe. The lesson was clear. In the most challenging environments, cooperation and partnership often succeed where individual effort fails. As scientists continued to explore hydrothermal vents around the world, they discovered that each vent field had its own unique community of species. Vents in the Atlantic had different animals than those in the Pacific.
Some species were found only at a single vent site, making them among the rarest animals on Earth. The study of these ecosystems also revealed something beautiful about the pace of life in the deep sea. While the vents themselves were dynamic and changing, the life around them moved with a serene deliberation that seemed almost meditative. The tube worms swayed in currents like underwater prayer flags. The giant clams opened and closed their shells with the patience of creatures that measured time in decades rather than days. In discovering these underwater gardens, scientists had found not just new forms of life, but new ways of thinking about life itself. The deep ocean, once thought to be a biological desert, revealed itself to be full of hidden oases where life had learned to bloom in the most unlikely places, creating beauty and abundance in realms of crushing pressure and eternal darkness. To truly understand the gentle giants of the abyss, we must first comprehend the extraordinary world they inhabit, a realm where the very concept of gentle takes on meanings impossible to imagine on the surface. In the deep ocean, gentleness is not just a behavioral trait, it's a survival strategy perfected over millions of years of evolution in Earth's most stable and demanding environment. The physics of the deep ocean creates conditions that naturally favor gentle, efficient movement over rapid, energy-intensive activity. Water is 800 times denser than air, and this density increases with pressure as we descend into the abyss. At depths of 4,000 meters, the water around our gentle giants has a viscosity that makes every movement feel like swimming through honey. This resistance means that explosive bursts of speed waste precious energy, while slow, steady movements conserve resources for the long term. The largest of our gentle giants are the deep-sea jellyfish, creatures so massive and ethereal they seem to exist in a dream state. The lion's mane jellyfish of the Arctic deep can have a bell diameter of over 6 feet, with tentacles that trail for hundreds of feet behind them like living party streamers. But unlike their smaller, more aggressive surface cousins, these giants move with a hypnotic slowness that transforms swimming into meditation. Their bell-shaped bodies pulse with a rhythm so slow and regular it seems synchronized with some cosmic heartbeat. Each contraction takes several seconds to complete, pushing water with such gentle efficiency that they can maintain their position in the water column for hours with minimal energy expenditure. Watching one of these creatures navigate the abyss is like observing a living parachute drifting through underwater space, so delicate and translucent that they seem more like manifestations of the water itself than separate organisms. The bioluminescence of deep-sea jellyfish adds another layer to their ethereal beauty. Many species can produce waves of light that travel across their bells in slow, hypnotic patterns. These light shows aren't random displays, they're sophisticated communication systems that can convey information about species' reproductive readiness and territorial boundaries to other jellyfish miles away in the darkness. The crystal jellyfish, found in the deep Pacific, produces some of the most spectacular bioluminescent displays in the ocean. When disturbed, it creates a cascade of blue-green light that ripples across its transparent bell like aurora borealis trapped in living tissue. The light production is so efficient that these creatures can maintain their displays for hours without depleting their energy reserves, creating underwater light shows that can be seen from remarkable distances in the clear, dark water of the abyss. Even more remarkable are the siphonophores, colonial organisms that challenge our very definition of what constitutes a single animal. The Portuguese man-o'-war that occasionally washes up on beaches is actually a relatively small example of this group. In the deep ocean, siphonophores can reach lengths of over 150 feet, making them among the longest animals on Earth. But calling a siphonophore a single animal is somewhat misleading. These creatures are actually colonies of hundreds or thousands of individual organisms called zooids, each specialized for a particular function. Some zooids form the gas-filled float that maintains buoyancy, others are specialized for feeding, still others for reproduction or defense. The entire colony moves through the water as a coordinated unit, like a living underwater train with each car serving a different purpose. The deep-sea species Praia dubia exemplifies the gentle giant lifestyle. This transparent siphonophore drifts through the water column like a living ribbon, its body so delicate that it can be damaged by the slightest turbulence. Yet this apparent fragility is actually a sophisticated adaptation to the calm, stable environment of the deep ocean. In a world where energy is scarce and movement is expensive, evolution has favored creatures that are so efficient they seem almost insubstantial. The feeding strategy of these gentle giants perfectly reflects their environment. Rather than actively hunting prey, most rely on passive feeding techniques that require minimal energy expenditure. Deep-sea jellyfish spread their tentacles like living fishing nets, drifting through the water and capturing whatever small organisms happen to encounter their stinging cells. This strategy works because the deep ocean, despite appearing empty, actually contains a dilute but steady supply of small prey organisms. The giant tube worms of hydrothermal vents represent a different type of gentle giant, one that has achieved remarkable size, not through active feeding, but by forming partnerships with microscopic organisms. These worms, which can grow to 8 feet in length and live for over a century, have no mouth, no gut, and no conventional digestive system. Instead, their bodies are filled with chemosynthetic bacteria that convert the toxic chemicals from hydrothermal vents into usable energy. This symbiotic relationship allows the tube worms to achieve remarkable sizes while expending virtually no energy on hunting or foraging. They simply extend their bright red feathery gills into the mineral-rich water and let their bacterial partners do the work of converting chemicals into food. The result is a creature that embodies the principle of gentle efficiency. In the eternal darkness of the abyss, light becomes the universal language, and the gentle giants of the deep ocean are fluent speakers in this luminous tongue. Bioluminescence, the production of light by living organisms, transforms the deep sea into a vast concert hall, where creatures communicate through symphonies of living light that would make any human light show pale by comparison. The chemistry of bioluminescence is elegantly simple yet remarkably sophisticated. Most deep-sea creatures produce light through a reaction between a compound called luciferin and an enzyme called luciferase, often with additional proteins that modulate the color and intensity of the light produced. This biochemical reaction is so efficient that nearly 100% of the energy goes into light production, with virtually no waste heat, a level of efficiency that far exceeds any human-made light source. But the true magic of deep-sea bioluminescence lies not in its chemistry, but in its poetry. Each species has evolved its own unique light language, creating patterns and colors that serve specific purposes in the lightless world of the abyss. The result is an underwater aurora that plays out in slow motion, with each flash, pulse, and glow carrying meaning that we're only beginning to understand. The giant Siphonophore arena creates one of the most spectacular light displays in the deep ocean. As this creature drifts through the water, it can illuminate sections of its 100-foot-long body in sequence, creating waves of red light that travel along its length like a slow-motion lightning bolt. The red light is particularly significant because most deep-sea creatures cannot see red wavelengths, making this a kind of stealth illumination that allows the Siphonophore to see without being seen. The deep-sea jellyfish, Atolla, has evolved perhaps the most dramatic bioluminescent defense mechanism in the ocean. When attacked by a predator, it creates what marine biologists call a burglar alarm, a brilliant circular display of blue light that radiates outward from its bell like an underwater lighthouse beacon. This spectacular light show serves two purposes. It confuses the immediate predator and attracts larger predators that might be interested in eating whatever is attacking the jellyfish. Watching an Atolla's burglar alarm display is like witnessing a living fireworks show in slow motion. The light begins as a small point and expands outward in perfect concentric circles, creating an underwater halo that can be seen from remarkable distances in the clear water of the deep ocean. The entire display lasts for several minutes, during which the jellyfish continues to pulse its bell with normal swimming motions, creating a hypnotic combination of defensive signaling and graceful locomotion. The vampire squid has evolved one of the most sophisticated bioluminescent systems in the deep ocean. Its body is covered with photophores, light-producing organs that can be controlled individually or in groups to create complex patterns. When threatened,
The vampire squid can produce clouds of bioluminescent mucus that glow for several minutes, creating a decoy cloud while the squid escapes into the darkness. But the vampire squid's light production isn't limited to defensive purposes. These creatures also use bioluminescence for communication, creating patterns of light along their arms and body that may convey information about species identity, reproductive status, or territorial boundaries. The patterns are often subtle and brief, like Morse code transmitted through living tissue, requiring careful observation to detect and interpret. The lanternfish, though relatively small compared to other deep-sea creatures, create some of the most coordinated bioluminescent displays in the ocean. These fish travel in schools of thousands of individuals, and when the entire school produces light simultaneously, the effect is breathtaking. The coordinated flashing creates underwater constellations that pulse and shift as the school moves, turning migration into a moving light show that can be detected by underwater sensors from miles away. Each lanternfish species has its own unique pattern of photophores, creating what marine biologists call license plates, species-specific arrangements of lights that allow individuals to identify their own kind in the darkness. These patterns are so distinctive that researchers can identify species simply by photographing their bioluminescent displays, without needing to capture the fish themselves. The deep-sea anglerfish has perhaps the most famous bioluminescent adaptation, the glowing lure that dangles in front of its mouth like a fishing rod with a living bait. But what many people don't realize is that this lure is actually a symbiotic organism, a colony of bioluminescent bacteria that live in a specialized organ on the anglerfish's head. The fish provides nutrients and shelter for the bacteria, while the bacteria provide a steady, controllable source of light for attracting prey. The relationship between anglerfish and their bacterial partners is so intimate that the bacteria cannot survive outside their host, and the fish cannot produce light without their bacterial symbionts. It's a partnership that demonstrates how cooperation can create capabilities that neither organism could achieve alone, turning the anglerfish into a living lighthouse in the depths of the ocean. The giant deep-sea jellyfish Deepsteria creates one of the most ethereal bioluminescent displays in the abyss. This transparent creature looks like a living plastic bag drifting through the water, but when stimulated, it produces waves of blue-green light that travel across its bell-shaped body like aurora trapped in gelatin. The light patterns seem to serve no obvious purpose. They're too brief to be effective for defense and too random to be clear communication signals. Instead, they appear to be an almost artistic expression of the creature's response to its environment. The crown jellyfish, Atala, has evolved a particularly sophisticated approach to bioluminescent communication. Rather than producing random flashes of light, these jellyfish can create specific patterns that vary with the situation. A gentle pulse might indicate contentment or normal activity, while rapid, intense flashing signals distress or territorial warning. The complexity of these light languages suggests that deep-sea creatures may have more sophisticated communication systems than we previously imagined. Some deep-sea creatures use bioluminescence not for communication or defense, but for hunting in ways that demonstrate remarkable intelligence and patience. The cookie-cutter shark, a small but notorious deep-sea predator, uses bioluminescent patches on its underside to mimic the silhouette of smaller fish when viewed from below. Larger fish, thinking they're approaching easy prey, instead encounter a predator that takes circular bites from their flesh before disappearing back into the darkness. The coordination of bioluminescent displays across different species creates what marine biologists call living galaxies, areas of the deep ocean where multiple species are producing light simultaneously, creating complex, ever-changing patterns that seem to have their own rhythm and logic. These underwater light shows can last for hours, with different species contributing their own unique notes to a symphony of illumination that plays out in the eternal darkness. The deep-sea mushroom jellyfish, Crossota, creates perhaps the most hypnotic bioluminescent display in the ocean. As it swims, it produces steady pulses of light that travel around the rim of its bell like a slow-motion neon sign.
The pulses are perfectly timed with its swimming movements, creating a coordination between locomotion and illumination that seems almost choreographed. Watching a group of these jellyfish swimming together creates the impression of underwater UFOs drifting through space, the bioluminescent plankton of the...
But our journey into the abyss is not complete without exploring one of the ocean's most extraordinary phenomena: the daily vertical migration that connects the deep ocean to the surface world above. Every single night, the largest animal migration on Earth takes place not across land or through the air, but through the water column of the ocean. As billions of creatures rise from the depths toward the surface in a synchronized dance that has been occurring for millions of years. This migration is so massive that it was first detected not by marine biologists, but by naval sonar operators during World War II. They discovered what they called the deep scattering layer, a mysterious zone in the water that seemed to rise toward the surface each evening and sink back into the depths each dawn. For years, military scientists thought this might be some kind of underwater landscape that defied the laws of physics, moving up and down through the water column on a daily schedule. It wasn't until decades later that marine biologists realized they were observing the greatest migration on Earth, a daily journey undertaken by countless small fish, squid, jellyfish, and crustaceans that spend their days in the safety of the deep ocean and their nights feeding in the productive surface waters above. This vertical migration involves more biomass than all the terrestrial migrations combined, yet it occurs entirely out of human sight, in the three-dimensional space of the ocean. The lanternfish are among the most abundant participants in this nightly journey. These small bioluminescent fish spend their days at depths of 1,500 meters, where they remain relatively safe from visual predators in the dim twilight zone. But as darkness falls on the surface, they begin an epic ascent that can cover over half a mile of vertical distance, rising to within a few hundred feet of the surface to feed on the rich plankton communities that thrive in the upper water column. The scale of this migration is almost impossible to comprehend. In some areas of the ocean, the biomass of migrating lanternfish exceeds that of all human beings on Earth. They travel in schools that can extend for miles, creating underwater rivers of life that flow upward through the darkness with the precision of a well-choreographed ballet. But the lanternfish don't make this journey alone. They are joined by an incredible diversity of deep-sea creatures, each following their own schedule and targeting their own preferred feeding zones. Deep-sea squid rise through the water column like living torpedoes, their chromatophores flashing in complex patterns that may help them coordinate their movements in the darkness. Jellyfish of countless species drift upward like living parachutes, their transparent bells pulsing with bioluminescent rhythms that create underwater aurora as they ascend. The vampire squid, those gentle cephalopods we met earlier, participate in a modified version of this migration. Rather than rising all the way to the surface, they move between different deep water zones, following the movements of the marine snow and organic particles that form their primary food source. Their migration is more subtle than that of the lanternfish, but no less precisely timed to the daily rhythms that govern life in the ocean. Even some of the gentle giants we've encountered participate in these vertical movements. Certain species of deep-sea jellyfish, despite their massive size, can adjust their buoyancy to rise hundreds of meters through the water column each night. Their movements are so slow and gradual that they seem more like geological processes than animal behavior, but over the course of hours, these giants can travel from the abyssal depths to the twilight zone above. The coordination required for these migrations is remarkable. Without any central command structure, billions of individual organisms somehow synchronize their movements to create a coordinated mass migration that occurs with clockwork precision every single day. The trigger for this movement appears to be the changing light levels at the surface, but the creatures beginning their ascent from the deep ocean are rising from depths where surface light never penetrates. This suggests that many deep-sea creatures maintain internal biological clocks that remain synchronized with the surface day-night cycle despite living in perpetual darkness. Their circadian rhythms, evolved over millions of years, continue to tick in rhythm with the rotation of the Earth above, connecting them to solar cycles they never directly experience. The energy cost of these migrations is enormous. Swimming vertically through the water column requires much more energy than horizontal movement,
as creatures must work against gravity and the increasing pressure changes as they rise and fall. Yet the benefits of accessing the rich feeding areas near the surface more than compensate for the energy expenditure, allowing deep-sea creatures to tap into the ocean's most productive ecosystems while maintaining the safety of the deep. The migrations also create a biological pump that transports nutrients and energy from the surface ocean to the deep. Creatures that feed in the productive surface waters carry that energy back down to the depths when they descend, supporting the communities of organisms that remain in the deep ocean throughout their lives. This vertical transport of nutrients is crucial for maintaining the productivity of deep-sea ecosystems, connecting the entire ocean into a single integrated system. The predators of the deep ocean have evolved to take advantage of these migrations. Deep-sea fish and squid time their own activities to intercept the migrating animals, creating feeding opportunities that might not exist otherwise. Some predators position themselves at specific depths along the migration routes, like underwater toll booths collecting their fee from the passing travelers. The bioluminescent displays that accompany these migrations create some of the most spectacular light shows in the natural world. As millions of creatures rise through the water column, their combined bioluminescence creates underwater auroras that can be detected by satellites observing the ocean from space. The light patterns change throughout the night as different species begin and end their migrations, creating a dynamic light show that plays out across thousands of square miles of ocean. During the full moon, these migrations take on an even more magical quality. The moonlight penetrating the upper layers of the ocean interacts with the bioluminescence of the migrating creatures, creating silvery cascades of light that seem to connect the surface of the ocean to its deepest depths. The migrating animals appear to navigate partially by moonlight, adjusting their behavior based on the lunar phase and the amount of natural light available at the surface. The seasonal variations in these migrations reveal another layer of complexity in the deep ocean's rhythms. During different times of the year, the composition of the migrating communities changes as different species respond to variations in surface productivity, water temperature, and food availability. Some species that migrate year-round are joined by others that only participate during specific seasons, creating migration patterns that vary throughout the year like underwater seasons. Climate change is beginning to affect these ancient migration patterns. As surface water temperatures rise and ocean chemistry changes, the timing and composition of the vertical migrations are shifting. Some species are beginning their ascent earlier in the evening, while others are not rising as high as they once did. These changes could have profound effects on the ocean's biological pump and the transfer of energy between surface and deep waters. The study of these migrations has revealed that the deep ocean is far more connected to surface processes than previously understood. Rather than being isolated in their abyssal realm, the creatures of the deep are participants in daily rituals that link them to the entire ocean system. Their nightly journeys toward the light create threads of connection that span the full depth of the ocean, weaving the surface and the abyss into a single, integrated ecosystem.
As we observe these migration patterns, we begin to understand that the gentle giants of the deep are not permanent residents of the abyss, but travelers who move through different oceanic realms according to ancient rhythms that connect them to the cosmic cycles of Earth's rotation and the moon's phases. Their movements remind us that even in the most remote and seemingly isolated environments, life remains connected to larger patterns and rhythms that span the entire planet. In recent years, scientists have begun to discover that the deep ocean holds secrets not just about life's adaptation to extreme environments, but about healing and regeneration that could revolutionize our understanding of medicine and recovery. The gentle giants of the abyss have evolved remarkable abilities to repair damage, regenerate lost tissues, and maintain health under conditions that would be lethal to most surface organisms. Their strategies for healing offer profound lessons that extend far beyond marine biology. The deep-sea environment, with its stable temperature, constant pressure, and minimal disturbance, creates ideal conditions for the slow, methodical processes of healing and regeneration. Many deep-sea creatures have evolved healing abilities that far exceed those of their surface-dwelling relatives, taking advantage of their calm, predictable environment to perfect the art of biological repair. Deep-sea sponges demonstrate some of the most remarkable regenerative abilities in the animal kingdom. These ancient creatures can regrow entire sections of their body from small fragments, a process that takes place so slowly and methodically that it seems more like geological formation than biological healing. When a glass sponge is damaged by a deep-sea current or the activity of other organisms, it begins a repair process that can take decades to complete, but results in structures that are often stronger and more beautiful than the original. The healing process in deep-sea sponges involves the mobilization of specialized cells that can differentiate into any type of tissue needed for repair. These pluripotent cells migrate to the site of damage and begin the slow process of rebuilding the sponge's intricate silica skeleton, often creating patterns that are more complex and elegant than those found in undamaged specimens. The process demonstrates that healing doesn't simply restore what was lost, but can create something new and improved. The vampire squid has evolved perhaps the most sophisticated damage control system in the deep ocean. When attacked by predators, these creatures can actually jettison damaged portions of their arms, allowing the predator to escape with a small piece while the squid retreats to safety. The remarkable aspect of this defense is not just the ability to lose body parts without fatal damage, but the squid's capacity to regenerate the lost tissue completely over a period of months. The regeneration process in vampire squid involves the activation of stem cell populations that remain dormant until needed. When tissue loss occurs, these cells begin dividing and differentiating, guided by chemical signals that ensure the regenerated structure matches the original in both form and function. The new tissue often displays improved capabilities, as if the regeneration process incorporates lessons learned from the original damage. Deep-sea corals have developed healing strategies that allow them to survive in environments where physical damage is inevitable. The constant movement of deep-sea currents, the occasional predation by fish and invertebrates, and the chemical challenges of their environment mean that coral colonies must constantly repair and regenerate damaged tissues. The healing process in deep-sea corals involves a sophisticated coordination between individual polyps and the colony as a whole. When damage occurs, neighboring polyps can share resources and cellular material to support the healing process, creating a community-based approach to recovery that ensures the survival of the entire colony. This cooperative healing demonstrates that in challenging environments, recovery is often a collective rather than individual process. The glass sponge gardens of the Pacific Northwest have provided scientists with unprecedented opportunities to study long-term healing processes in deep-sea organisms. Some of these sponges bear scars from damage that occurred decades or even centuries ago, yet the healing process continues slowly and methodically, with new growth gradually covering and incorporating the damaged areas. The study of these ancient healing processes has revealed that deep-sea organisms approach recovery very differently than surface animals. Rather than rushing to heal quickly, they invest time and energy in creating repairs that are more durable and resilient than the original structures. This approach to healing prioritizes long-term stability over short-term restoration, resulting in organisms that become stronger and more resilient with each recovery cycle. The biochemistry of deep-sea healing has attracted significant attention from medical researchers seeking new approaches to human healing and regeneration. Many deep-sea organisms produce unique compounds that promote tissue regeneration, reduce inflammation, and protect against infection in ways that could have applications for human medicine. Deep-sea bacteria associated with hydrothermal vents have been found to produce antibiotics that are effective against antibiotic-resistant pathogens that plague human medicine. These compounds evolved in environments where competition for resources is intense, and the ability to inhibit the growth of competing organisms provides a significant survival advantage. The collagen produced by deep-sea organisms has properties that make it particularly effective for medical applications. The constant pressure of the deep-sea environment has led to the evolution of collagen structures that are more stable and durable than those found in surface organisms, making them ideal for medical implants and tissue engineering applications. Some deep-sea creatures have evolved healing mechanisms that operate at the cellular level in ways that could inform cancer treatment. The controlled cell division,
and differentiation that occurs during deep-sea regeneration follows patterns that ensure healthy tissue growth while preventing the uncontrolled proliferation that characterizes cancer. The stress response systems of deep-sea organisms offer insights into how biological systems can maintain function under extreme conditions. These creatures have evolved cellular mechanisms that protect against the damage caused by high pressure, low temperature, and limited oxygen availability, creating biological systems that are remarkably resilient to environmental stress. The study of deep-sea healing has also revealed the importance of environmental factors in the recovery process. The stable conditions of the deep ocean, constant temperature, steady pressure, minimal disturbance, create an ideal healing environment that allows for the slow, methodical repair processes that characterize deep-sea regeneration. This understanding has led to new approaches in human medicine that emphasize the importance of creating optimal healing environments. Hyperbaric oxygen therapy, controlled temperature environments, and reduced stress protocols all draw inspiration from the principles observed in deep-sea healing. The deep-sea approach to healing also emphasizes the importance of time in the recovery process. Unlike surface organisms that must heal quickly to avoid predation or environmental challenges, deep-sea creatures can invest the time needed for complete and thorough healing. This approach often results in repairs that are superior to the original structures, suggesting that adequate healing time is crucial for optimal recovery. The community aspects of deep-sea healing offer insights into the social dimensions of recovery. Many deep-sea organisms heal through cooperative processes that involve entire communities working together to support individual recovery. This collective approach to healing suggests that social support and community involvement may be crucial factors in effective recovery processes. The bioluminescent aspects of deep-sea healing add another dimension to our understanding of recovery processes. Many deep-sea organisms increase their light production during healing, possibly as a way of communicating their status to other community members or as part of the biochemical processes involved in tissue regeneration. The psychological aspects of deep-sea healing, while difficult to study directly, suggest that these organisms have evolved mechanisms for coping with the stress and trauma associated with injury and recovery. The slow, methodical approach to healing observed in deep-sea creatures may reflect not just physical repair mechanisms but psychological strategies for dealing with damage and loss. The applications of deep-sea healing research extend beyond medicine to fields such as materials science, where the self-repair mechanisms of deep-sea organisms are inspiring the development of self-healing materials and structures. The principles observed in deep-sea healing could lead to the creation of buildings, vehicles, and infrastructure that can repair themselves when damaged. As our understanding of deep-sea healing continues to develop, we're discovering that these ancient organisms have much to teach us about recovery, resilience, and regeneration. Their approaches to healing, refined over millions of years in one of Earth's most challenging environments, offer insights that could transform our understanding of what it means to heal and recover in a world that often values speed over thoroughness, quick fixes over lasting solutions. In the perpetual darkness of the abyss, where time moves like honey and change occurs across geological epochs, some of the ocean's gentle giants have evolved memory systems that challenge our understanding of how biological organisms can store and process information across vast spans of time. These deep-sea memory keepers carry within their tissues and behaviors the accumulated wisdom of millions of years, creating living libraries that preserve information in ways that seem almost magical to surface dwellers. The ancient glass sponges of the deep Pacific represent perhaps the most remarkable example of biological memory storage in the ocean. Individual sponges that have lived for thousands of years carry within their silica skeletons detailed records of environmental conditions spanning multiple climate cycles. Each layer of growth represents a year or decade of environmental history, recording information about water temperature, chemical composition, and food availability with a precision that rivals human-made scientific instruments. Scientists studying these ancient sponges have discovered that they can extract climate information going back over 10,000 years,
making them among the longest continuous environmental records available on Earth. The sponges' skeletons serve as biological libraries, storing information about ocean conditions that predates human civilization by millennia. But the memory capabilities of these sponges extend beyond simple environmental recording. Research has shown that glass sponges can alter their growth patterns in response to environmental changes, suggesting that they possess a form of biological memory that allows them to anticipate and prepare for future conditions based on past experiences. Sponges that have survived previous warming periods, for example, begin altering their skeletal structure in ways that will help them survive similar conditions in the future. The Greenland sharks that patrol the Arctic deep carry within their tissues a different kind of memory, genetic memories that span multiple human generations. With lifespans exceeding 400 years, individual sharks serve as living bridges between different historical periods, carrying in their bodies the chemical signatures of environmental conditions that existed centuries ago. The proteins in Greenland shark eye lenses, which are formed during the shark's youth and never replaced, serve as time capsules that preserve information about the ocean chemistry and food webs that existed when the shark was young. Scientists can analyze these proteins to reconstruct environmental conditions from centuries past, using the sharks themselves as living instruments of historical measurement. But perhaps most remarkably, Greenland sharks appear to possess behavioral memories that span their incredibly long lifespans. Individual sharks have been observed returning to the same feeding areas and following the same migration routes for decades, suggesting that they can remember and navigate complex three-dimensional routes through the Arctic Ocean across time frames that exceed human lifespans. The deep-sea coral communities demonstrate another form of biological memory, collective memory that operates at the level of entire ecosystems rather than individual organisms. Coral colonies that have grown for thousands of years create community memories that guide the behavior of the entire reef system. When environmental conditions change, established coral communities can guide the responses of newer colonies, sharing chemical information about successful survival strategies through the water column. Young corals settling near ancient colonies benefit from this accumulated wisdom, growing in patterns and developing structures that reflect lessons learned by previous generations. The bamboo coral forests of the deep Pacific have evolved sophisticated memory systems that operate across multiple timescales. Individual coral colonies remember seasonal patterns in current flow and food availability, adjusting their growth and feeding behavior based on past experience. But the forest as a whole maintains longer-term memories that span centuries, preserving information about rare events like major storms, volcanic eruptions, or climate shifts. These forest-level memories are encoded in the spatial arrangement of coral colonies, the patterns of growth and reproduction, and the chemical communications that flow between different parts of the community. The result is an ecosystem-scale memory system that allows entire coral forests to adapt to environmental changes based on collective experience spanning hundreds of years. The tube worm communities around hydrothermal vents demonstrate how memory can operate in environments where individual lifespans are relatively short but community continuity spans much longer periods. Although individual tube worms may live for only decades, the communities they form can persist for centuries, maintaining collective memories about vent activity, predator patterns, and food availability. These community memories are preserved through chemical signals embedded in the tube structures that worms leave behind when they die. New generations of worms can read these chemical records, learning about past environmental conditions and adjusting their behavior accordingly. The result is a form of intergenerational memory transfer that allows vent communities to benefit from the experiences of previous generations. The giant Pacific octopuses that inhabit the deep ocean demonstrate individual memory capabilities that are remarkable for invertebrates. These intelligent cephalopods can remember complex three-dimensional routes through underwater terrain, returning to specific hunting grounds and shelter sites after absences of weeks or months. Even more remarkably, Pacific octopuses appear to be capable of learning from the experiences of other octopuses, suggesting a form of cultural memory that operates within octopus communities.
Young octopuses can learn hunting techniques, predator avoidance strategies, and territorial boundaries by observing the behavior of older, more experienced individuals. The memory systems of these octopuses are particularly impressive given the challenges of their deep-sea environment. In a world without visual landmarks and with currents that can shift the positions of mobile objects, the ability to create and maintain accurate mental maps requires sophisticated cognitive abilities. The deep-sea anglerfish have evolved memory systems that are specifically adapted to their sparse, unpredictable environment. These fish can remember the locations of successful hunting events across vast areas of ocean, returning to productive feeding grounds after intervals of months or years. The memory capacity of anglerfish appears to be enhanced by their extremely low metabolic rates, which allow them to invest more energy in maintaining neural structures than would be possible for more active fish. Their brains show specializations for spatial memory and environmental pattern recognition that exceed those found in most other fish species. Some deep-sea creatures have evolved memory systems that operate on multiple time scales simultaneously. Deep-sea jellyfish, for example, can remember short-term information about local current patterns and food availability, while also maintaining longer-term memories about seasonal migration routes and breeding cycles. These multi-time scale memory systems allow deep-sea organisms to respond appropriately to environmental changes that occur on different temporal scales, from daily fluctuations in food availability to century-scale climate cycles. The study of deep-sea memory has revealed that these organisms have evolved information storage and processing capabilities that in some ways exceed those of more complex surface animals. The stable environment of the deep ocean, while challenging in terms of energy and food availability, provides ideal conditions for the development of sophisticated memory systems. The lack of environmental disturbance in the deep ocean means that information stored in biological memory systems remains relevant for much longer periods than in more dynamic surface environments. A deep-sea organism can invest in remembering environmental patterns because those patterns are likely to persist for long enough to make the memory valuable. The discoveries about deep-sea memory have implications for our understanding of consciousness and intelligence in the ocean. The sophisticated memory capabilities observed in deep-sea organisms suggest that these creatures possess cognitive abilities that we are only beginning to appreciate. The collective memory systems observed in deep-sea communities challenge our assumptions about where intelligence resides in biological systems. The ability of coral reefs, sponge gardens, and vent communities to maintain and utilize collective memory suggests that intelligence and consciousness may be properties of entire ecosystems rather than just individual organisms. The temporal scales of deep-sea memory also offer new perspectives on the relationship between memory and time. While human memory typically operates on scales of days to decades, deep-sea organisms maintain memories that span centuries or millennia, creating forms of biological consciousness that operate on geological timescales. These discoveries are influencing fields beyond marine biology, from artificial intelligence to philosophy. The memory systems of deep-sea organisms offer models for creating artificial memory systems that can operate efficiently over very long time scales, while their collective memory capabilities suggest new approaches to distributed information processing. As we continue to study the memory capabilities of deep-sea organisms, we're discovering that the abyss is not just a repository of ancient life forms but a vast library of biological memory that preserves information about Earth's history in ways that no human archive could match. In the gentle giants of the deep, we find not just remarkable adaptations to extreme environments but sophisticated information processing systems that carry within them the accumulated wisdom of deep time itself.